we had explored thoroughly the idea of a force. So actually the idea of a force is something that's pretty old, but in the current formation, there's the current conceptualization of force actually started with, if you remember, Kepler. Okay, the idea of something pushing or pulling physically, that's okay, that's pretty old. That's almost Aristotelian, if not older than that. But there is one kind of force, which is what we call as a non-contact force, which first came into existence in terms of Kepler figuring out that in the solar system, the way the planets move seemed to suggest that it was the sun from which was emanating a force. This is how he put it: emanating a force that kept the planets in their circular orbit. Of course, the orbits were not circular. Kepler himself did the work that suggested that the orbits were elliptical. But basically, the idea comes that in forces you have contact forces and then you have non-contact forces. Okay? And it is the non-contact forces that create considerable difficulties. And I'm saying it non-trivially. One is that it is difficult to understand how an object can exert a force on another object without actually making contact. And this problem actually went all the way to Einstein, and it became a problem for his general theory of relativity. This fact that that there is a non-contact force that acts between two objects, specifically gravity, which acts over a distance. He apparently called it spooky action over a distance. Some of you have read about this and you know this very well. So I'm just saying this in order to contrast the kinds of forces. The simplest simplest difference would be to break it up into contact forces, non-contact forces. Okay. Now, moving on from Kepler's work, Galileo, whom we also visited as a part of the history of physics approach, then did the work with the inclined planes. If you remember that particular experiment, if you roll down an object down an inclined plane, then the object on the other side attempts to get to the same height, and if you keep increasing the length before it reaches the same height, then in every case the object, provided you have made a sufficiently smooth inclined plane, will attempt to reach the same height. Now, the crucial breakthrough that Galileo made, of course, was as a thought experiment. So he said, if this were to be extended infinitely, in the sense that if you could make an inclined plane that were infinitely long, then an object which has been rolled down this should go an infinite distance before it reaches the height that it started from. The fact that that does not happen in real life seemed to indicate to him that there is a force which prevents it from moving. And this answered a very crucial question about the state of motion of objects. Okay, there was this great debate based on questions that came from astronomy. Objects' natural state is rest or motion. Okay, and this was a kind of chicken and egg question which lasted for a very long time. If you start thinking carefully about it, you will still come back to the same idea, whether it is at rest or its motion. How do we know that objects which are at rest were always at rest? what caused it to come to a rest, or whether objects that are in motion, how do you know that they are in motion? Only because no force acted on them. But anyway, it was a breakthrough, and then we came to Newton, who then took this idea up and built it into the concept of inertia, giving us the first law, okay, which was that every object is in a state of rest or motion unless and until an external unbalanced force acts on it. The concept of inertia being that that is the property of an object, often equated to its mass but not necessarily so, where because of that property, object which is in motion will always remain in motion, and an object which is at rest will always remain in rest unless and until an external unbalanced force acts on it. So we are going to examine that particular phrase, external unbalanced force. Okay, what does that mean? That means that if you have an object, and I reintroduce, we can have a round of applause for the reintroduction of our famous, what is it called? I forgot. Mysterious.
Mystery box.
Mysterious box.
It's called mystery box.
You people like to call it mystery box, is it? I don't, I doubt if I ever called it a mystery box.
You did.
I called
Eighth grade was mystery box.
Yeah, I remember very well in 8B it was mystery box.
the kind of thing
I
remember.
have my 8th grade notebook. That says mystery box.
You might have wrongly noted it down. Mysterious box sounds better than mystery box man. Mystery man. How does it sound? Instead, if you say mysterious man, there's more drama in the word mysterious than mystery. Okay, so so carrying on, mysterious box, yeah, makes more sense too. I agree. All these people, they make no sense whatsoever. So this mysterious box, a box which has essentially no friction acting on it, it is infinitely rigid. That means it cannot be deformed by forces acting on it, and sometimes does not have mass either, but we don't need to worry about that now. This box will therefore remain at rest as it is now and until an external unbalanced force acts on it, which means you could apply a force. Forces, incidentally, I remind you, are represented by arrows. They are vector quantities, which means they have magnitude, and it's also important to give their direction for us to understand completely what that force is going to achieve. So if you take, let's say, a 50 Newton force, well, okay, I have not defined what is a Newton, so let me not use the word Newton. If you use a 50, what can I call it? A 50 unit force. Okay, so I have not figured out a way to talk about the unit of forces yet, so I just say 50 units of force, whatever that may be. We'll come to that a little later. And an equal amount of force acting from the other side, 50 unit force. Okay, then that object, although it has forces acting on it, would not budge an inch. Okay, so we can say that this object will be in a state of rest even if forces act on it, because their forces are not unbalanced. Whereas if you have an object on which there is a 50 unit force acting from one side, and that looks like what? That looks like a 20 unit force acting from the other side, then we can say that there is a balance of forces in this case. 50 Newton subtracts from the 50 Newton. It's like saying somebody pushing strongly from this side and somebody pushing weakly from the other side. So what you will end up having is you will have a resultant force of about 30 unit force. Okay, I'm just creating a unit for force, because I haven't defined a Newton yet. I'll come to that. Okay, and this will then cause the object to start moving in this direction. So the motion will take place in this direction. So therefore we can say conversely that if an object is moving, then there is a possibility that there is a force acting on it. Now, why do I say there is a possibility? Because there are two types of ways in which you can define the motion of an object. When an object is at rest, right, we call this as an equilibrium. Okay, so I need to develop this idea a little bit. So in this case, we say that the two forces are opposed to one another, right? So we say the sum total of forces. Now, if you remember this concept, sigma F, okay, there we say that if we take this force to be acting on a positive and therefore this force to be acting in a negative direction, then we say that the two forces actually cancel each other out. Okay, this kind of situation, when the object is at rest, not moving, is called as an equilibrium. Where do I write that? I have to erase the board. And this equilibrium of force specifically is called a static equilibrium. Now, it is possible, let us say, that an object is in motion. So I get rid of this. So the object is in motion. Okay. And now what happens is that you have a force acting on this object, let's say from that direction. Okay, why complicate it? I'll just put it from this direction and an equal force acting from this direction. And let this be some 10 unit force and this is another 10 unit force. Of course, if we keep this as positive, then this becomes negative. Now the question is, what happens to the motion of that object? So I would like the Aristotelians and the non-Aristotelians to respond.
It'll rotate is like,
Sorry?
I don't know. I'm not sure.
There is an object that is moving in this direction. And let us say this is one of Galileo's objects. It has been set in motion. It's a mysterious object, no friction. So it is happily moving along until two forces suddenly came and caught it from opposite sides.
Is it exactly opposite?
Exactly opposite, although it doesn't look like that, but we assume that they are acting exactly. So no toppling is possible.
Okay. Then.
So what happens to the velocity of this object? It is here. What?
Shouldn't it remain?
They'll just cancel each other out.
Ah,
Same.
okay. So some people have moved from their Aristotelian thinking.
It won't accelerate.
So it will not change its state of motion. It will remain in the same speed with which it was moving prior to this. Okay. So this kind of situation is also an equilibrium. Okay. Except that this is an equilibrium called as dynamic equilibrium. Okay. So therefore, now we can say that what if there isn't a dynamic equilibrium? What if the situation is such that the object is being acted upon by two unequal forces. So there is a larger force on this side and there's a smaller force on this side. Okay, and this looks roughly like 4 times the force. So I'll call this 40 unit force, and this is 10 unit force. Okay, then what happens is that there is a resultant force. So you
Yeah.
subtract 10 from the 40. Okay, and let's say that it used to be moving. It was moving. It looks like it's flying, but it's moving. Inaccuracy in drawing, beg your pardon. And the resultant force, this 10 Newton, I subtracted from this. Okay, so you got 30 unit force left over. Sorry, I keep saying Newton, I should be saying unit force. Then what will happen is that there is a net force acting on it. So the sigma F in this case is not equal to 0. In fact, we know exactly how much it is. It is equal to plus 30 unit force. So now what happens is that the object will start to speed up. Okay, so from this idea comes our second what do you call it, law of Newton, which is that if you take an object, I think the object that we talked about, okay, I can take the same object. If anybody is not able to understand what is going on, you'd like to check with me, please stop us and ask your questions, okay? So don't go on for too long without being able to figure it out. I'll be happy to answer the questions. Now, this object is going to start going faster. What if I double the force acting on it? So I've got 60 unit force acting on this object. What can you say will happen to the speed of that object? Comparing situations A and B.
I don't know about speed, but it'll accelerate more. Like it'll
Yeah.
accelerate
So
double or something.
you can say therefore that in situation B, the rate at which it will change its speed is going to be more than the rate of A. And in fact, if everything else is exactly the same, then you can even say that it's probably going to double the rate at which its speed changes. Okay, I'm doing a very fast sort of, because we have come from first law to second law already. Something that typically takes us like 1.5 months to do in 8th standard. I'm like moving very fast. So again, I'm saying in case you're not able to follow, please stop us. So from this idea, and one more idea is there, which is that, okay, what if I did this? I create another situation. Now I double the mass of the object. So in this case, the mysterious box has mass, and let's say I double the mass of the object. The same amount of force I apply on this as in case B, 60 unit force, right? Then what can you say about situation C? So I'm asking in terms of rate of change of speed. In both cases, the speed with which it is going will increase, and it will increase as long as the force is acting on it, right? So it will start going faster and faster and faster. Here also it will start going faster and faster and faster. So you say that in this case, the rate of change is going to be more than the case over here. What if I double the mass? That means I have doubled the inertia. So how do you compare C with A and C with B?
I think A and C will be the same.
I think you speak too loudly.
What?
Sorry. Yes, you're right. A and C will be exactly the same because both have been increased by a factor of 2, right? So from this, Newton formulated that the acceleration experienced by a body, so now I'm introducing the concept, acceleration, rate of change of speed, is directly proportional to the force acting on it. Okay, and the acceleration produced on a body is directly proportional to the mass of the object. So if the masses were similar or the same, then if you apply a force on an object, then you will produce a proportional acceleration on it. Whereas if the force was the same, but you changed the mass, that means that the acceleration will be inversely proportional to the mass, which means that the more the mass, less the acceleration. Is all this more or less falling in the right place? We did something like about 150 years of physics in one go, and something that takes me like 2 months to pick it up, but we have done this before, so you should be familiar with this. Is it all clear? Shall I move on? Finally, I define what is a force. Okay, so then I can say that acceleration is directly proportional to F upon m, and by choosing units as per our convenience, I remember telling you this story, it is just that there was no unit for force until that point of time. So what we said was, if you take an object of mass 1 kilogram and it got an acceleration of 1 meter per second square, 1 meter per second, then we can define the force as being one something. That something was what we called as a Newton, in honor of the scientist who gave us this relationship. So therefore, by doing this, what we did was we eliminated the constant of proportionality, that annoying, irritating thing, right? Because if all of them were ones, acceleration is also one, mass is also one, force is also one, so k will also be one. Therefore, we get the relationship A is equal to F by m, which is more commonly written as F equals ma. And this defines what your force eventually is. A force is something that when act on a body of mass produces an acceleration. And this has to be, of course, looked at in conjunction with the first law. The force has to be something that is external, unbalanced. Only then it will produce an acceleration on the mass. Okay, so that brings us up to the doorstep of where I want to take off for the concept of moments and so on. So I think it's time we can stop now. But if there are any questions that anybody would like to ask, since it's lunchtime after this, you can stay back. We can have a quick discussion. I can clarify anything that you did not catch.